Hi all, this is Mr. Yeager looking at physics with magnetism today. This is a pretty brief unit, primarily a conceptually bound section where we're only going to get into some math when we start looking at what are called transformers. So here we go. Okay. So what is magnetism itself? Obviously this is connected with electricity. We'll see in a moment in one of the sections. Excuse me. All right. The magnetism itself is an attraction or repulsion. Excuse me. An attraction or repulsion due to the arrangement of the electrons themselves. Okay. What we don't have to get into this much detail with it. What's happening here is magnetism is related to the spin of the electrons. We know electrons can spin clockwise or counterclockwise. It turns out if you align all these electrons and make them all spin the same direction, it'll create a magnetic field. All right. And from that, we can then obviously create these magnets themselves. So, with a magnet, we know it'll create a magnetic force. All right. We can either be a push or a pull. Like poles will repel. Okay. Unlike poles attract. The poles of a magnet we say are north and south. All right. That again basically just goes with the direction that it's spinning. The electrons are spinning. So north and north will repel. South and south will repel. But north and south will attract. If you happen to break a magnet, it doesn't destroy it yet. Okay, it obviously might make it weaker because it's going to be smaller, less electrons involved. But what will happen is it will make two new magnets. All right, those two new magnets will create a new north and south pole because those electrons are still pointing in one direction in terms of their spin. So even if you break it in half, now you just have two smaller magnets. The magnetic field. All right. This is the area around that magnet which will create a force. So the magnetic field is what will create, the magnetic field is what will create the force. Just like a gravitational field creates a force. All right, this would be this would be considered again what we call a field force. You don't need to be touching the magnet to feel the force on it. All right, and field lines are always coming from the North Pole and wrapping around it going towards the South Pole. Okay? They always come out from the north and go into the south. Okay? So right here we draw that arrow going around backwards like that. Those field lines are always drawn north to south. What this is showing right here is basically what compasses do. Compasses will always point in the direction of the magnetic field. Okay? I'm going to change color here so we can see it. Okay. All right. So compasses always point in the direction of the magnetic field. All right. So compasses actually always point to a magnet's south pole. If I place a compass right here, if I place that's going to be tough to see. If I place a magnet right here, what I would see is it would actually be pointing this direction. I would be pointing on toward the South Pole. All right, we'd actually have that magnet wrap around and point in the direction of the field itself. So if I gave you a problem where you have a blank magnet and I give you a compass, all right, and it's pointing this direction, and I go, which side, A or B, is the North Pole? You'd have to say the A side because the field must be coming out, wrapping around, and going towards the South Pole. So the compass always points in the direction of a magnetic field, all right, itself. All right. Before we jump to this, I just have one other thing then to basically go over with that. So if we talk about the Earth, if we say the Earth, if you've ever used a compass always points towards the north. A compass always points towards the north. No matter where you are, that compass will point geographically. Sorry, I should say that clearer. Geographically north. So one question that is often asked, okay, so compasses point geographically north. All right. That means, where is the magnetic North Pole? So this is the geo North Pole. This is the south pole, the geographic. If the compass is always pointing towards the geographic north pole, what does that mean? We'll draw the field lines. That means the field lines must be traveling up and around towards the North Pole, which means that they are coming from the South Pole. What does that tell you about the South Pole? It is the magnetic South Pole and the, oh sorry, I just did that backwards. It is the magnetic North Pole, while the geographic North Pole is the magnetic South Pole. You can see why this gets confusing, okay? So the geographic pole and the magnetic poles are actually opposite to each other at this time. And I say at this time because in Earth's history, the magnetic field has reversed itself, all right, over time. What actually will cause that? I can't really say. But we have, in the fossil record, we have actually investigated which way in certain fossil layers all the electrons are pointing, all the magnetic fossils are pointing. I say magnetic fossils, the magnetic rocks. And it turns out we actually see at different layers that they actually end up pointing different directions during different eons. Okay? But at this time, the geographic North Pole is the magnetic South Pole. So guess what? If we happen to flip sometime, all of a sudden everybody's compass is now going to point towards the south. Okay? So it might happen. Who knows? All right? So uses of magnets. So there's not many, there's plenty of uses. We only go over a couple though. The primary use for a magnet, okay, is actually when we create what's called an electromagnet. This is where we can use it in many, many different ways. So what you saw earlier, these little bar magnets that we call them, north-south, these are called permanent magnets. An electromagnet is a temporary magnet. It's one that you can turn on and off. A permanent magnet is always on. All right? So an electromagnet is something very useful because you can switch it on or off. And it's created, the simplest version is basically where you coil wire around an iron core, around a good metal core. Okay? And so when you create this, I think I got a picture of it, it will act like a magnet when you allow current to run through that wire. So when you let that wire go and you let the current start going vroom, 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 vroom around that, it actually starts creating a magnetic field. All right? And something that, hey, you disconnect it, magnetic field's gone. So this is very useful. It's something that you can turn on and off. All right? Anything that, whoa, there goes my voice. Anything that produces sound has an electromagnet in it. All right? So again, one classic question will be, which of the following things has a magnet in it? Anything that produces sound, speakers, radios, cell phones, all right, headphones, all those things have an electromagnet in it. All right? And what they do, we'll learn about this in the following unit, is they create what's called a longitudinal wave. When you turn this on and off, you actually cause the magnet to the sound piece to vibrate. All right, when it's flipped on, it moves out. When it's turned off, it flips in. When it turns on, it goes out. When it turns off, it goes in. All right, and so when you do that with a battery, basically it will keep on reversing that magnetic field, and then create this pumping motion that creates sound for you to use. Okay, it creates that because there's this attraction and repulsion from the speaker going into it. Motors. Okay, we talked about motors when we did energy. Motors is anything that we convert some other form of energy, usually electrical, into mechanical. Okay, motors, yep, electrical to mechanical energy. All right. This is done because if we add the electricity to it, we can basically create this magnetic field around the center core again and basically make it start spinning. Oops, let me go back to that again real fast. You're not going to have to explain this in too much detail. Basically what you have is a motor essentially is a device that you have these permanent magnets inside of it, all right? And then in between you have the electromagnet. I'm just going to write EM. I'll write PM on the other ones. And what happens is when you have that electricity run through the electromagnet, it creates that magnetic field, and then basically one magnet pulls the electromagnet one way, while the other one makes it spin the opposite, and basically this thing just starts rotating. Okay, the electromagnet starts rotating. Well, if that's connected to some sort of metal piece in a wheel, well, guess what? That wheel will start to rotate itself too. All right. So with the constant change of the magnetic field, it creates that attraction and repulsion, makes that the electromagnet itself begin to rotate between the permanent magnets, which again can be connected to some other piece to make it start moving, changing electrical energy into mechanical energy. All right. The other one I'll mention, generators. Okay, generators also is a use for magnets, and again uses the electromagnet, but actually makes it go the opposite direction. It turns out if you spin that metal piece wrapped in wires between two magnets, it'll actually start creating electricity. It'll force electrons to go through the wires. Okay. So, how do we create? Oh, how about that? How do we create electricity? Okay. Well, we can do that with an electric generator. All right. And again, this is going to be the opposite, mechanical to electrical energy. What you have is you have this armature. The armature is the center piece, the electromagnet that's between these magnetic poles. All right. If we can then start making that thing rotate, we can basically start making the electrons in the wires start moving through the wires, creating a current. All right. That's all you need to know about that. That was pretty quick, wasn't it? Okay, so again, not much detail. Just know generators create electricity through magnetic and electrical components, essentially. Some other general terms. This kind of hits the number of different things. You've heard of DC and AC, or AC-DC, not the band. All right. DC stands for direct current. This is where current travels only in one direction. All you need to know is this is related to batteries. Dry cells are basically your standard battery. Okay, your standard AA, AAA batteries. All right, they do what's called a direct current. All that means is that the current will go only one direction. Okay, the whole time. Alternating current, AC, what happens here is this is really related to the generator. It will alter the direction of the current because depending on how the object might be spinning, the armature might be spinning, it will reverse the direction of the magnetic field and therefore the induction, the creation of those electricity. So this is something that we never see. Okay, this is occurring in all electrical outlets. We use AC electricity. That turned out to be the primary version of electricity that we use by power companies. Direct current, developed by Edison, ended up losing to Tesla and his alternating current, if you've recognized some of those names. So what's happening here is actually, we never see it because the current's so fast, but the electricity is turning on and off very, 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 very quickly because it has to switch directions. So it's traveling one way and then the opposite way. You can sometimes see this with TVs, all right, or maybe you have your video on the TV. All right, the video actually slows it down some, and you can see the flickering some basically as you have the alternating current. All right, but again, this is just definitions for you to know. DC is when it's traveling one direction. AC is when it's changing directions. All right, so this leads us to our last major topic: a transformer. All right, a transformer is how we increase or decrease the voltage. All right, that comes into your house. These are very, very important because power companies, they produce a huge amount of energy, but the thing is, you don't want that energy to come flying into your house. If you've ever had a power surge, that's because a transformer failed and you got too much electricity to your house, and what happens? Things basically burn out. I mean, it possibly even causes a fire, but basically your device gets overloaded and might get destroyed. It might die, but obviously break. And so a transformer is used to either increase or decrease this voltage coming to your house, or obviously in power companies to increase what they've already done. Okay? And so there's a couple pieces to the transformer. We have what's called the primary coil and the secondary coil. And what happens is we alter how many times we wrap the coil around the transformer. Okay? How many times we wrap it around the transformer. All right? And we do that because the more coils we have, that creates a stronger magnetic field. So I need to take a step back. Okay? I want to go back to one thing real fast. All right? Go back. All right, sorry. I want to go back to electromagnets real fast. There's one thing I forgot to quickly mention here. There are many ways to improve an electromagnet, and that's what a transformer is going to take advantage of. All right? The strength of the magnetic field basically depends on three things. There's three things you can do to increase the magnetic field, the strength of this magnet. All right? One of those is increase the number of coils. What we mean by that is wrap the wire around the iron core more times. Increase the number of coils. That's going to be the easiest method to increase the strength of your electromagnet. You can increase the current that runs through it. That's very possible. Obviously, a stronger battery will be a stronger magnet if you have more electrons running through it. And three, obviously, like we already said, a metal core. It is possible to use glass or even plastic and still create an electromagnet. It just won't be as good as a metal, because a metal, again, has the delocalized electrons. It helps to let those electrons move very, very freely. Okay? It's not an insulator, it's a conductor. All right? But these are your three ways that you can increase the strength of this electromagnet. So sorry about that, I forgot to mention it. So coils is a very, very important thing to think about. All right? So when we get to transformers, they basically utilize that. If I increase the number of turns, it's going to increase the voltage. The voltage will relate to the number of turns. All right? You can see even in my picture here, 100 turns, 120 volts. 200 turns, 240 volts. So the number of turns is directly related to the voltage that's going to be produced. So it's a 1-to-1 ratio. And so that leads us to a couple different types of transformers out there. We have what are called step-up transformers. This is where we increase the voltage, as the name implies. This is something where the secondary coil will have more turns. The secondary coil. All right? This is used by power plants. Then there are step-down transformers. These are usually in those little boxes in the neighborhoods or even possibly in front of your own house. All right? A step-down transformer is trying to decrease the voltage, so there's going to be fewer turns on the opposite side on the secondary coil. So this is often, step-ups are really only in power plants, so they can shoot that electricity out, because again, as we talked about, the longer it has to travel, the more resistance it faces, so they want to give it a good push. But when it reaches your house, you want to slow that down. You want to go, whoa, 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 whoa. Slow down, slow down, slow down. And even your appliances have transformers in them, usually plugs do, to even decrease that more for your individual device. So even what's coming out of the outlet is not necessarily what goes into your device. It's trying to control that. So we have a couple of equations. All right? We have essentially, okay, this is not meant to be equals. This is meant to be all related. The current in the secondary, okay, we're going to see is going to be, all right, sorry, wait a minute here. I'm seeing one mistake. Okay, that's what I'm looking for. Sorry about that. Okay, it's not clearly seen. What this is trying to show you is that the equation is, let's get rid of one equal sign. Ugh, causing problems. Apologies. All right. We're supposed to have a division between here. Division. That's there. We can get rid of these equal signs. All right. So this is your equation. Current in the secondary coil divided by current in the primary coil is equal to the voltage in the primary coil over the secondary coil, which equals the number of turns in the primary coil over the turns in the secondary coil. So the thing is, you're never going to use all three of these together. You're going to usually solve one side and then bring it over to the other. This is kind of the initial one that we talked about. The ratio between the voltage and the number of turns is directly related. We have both primaries on top, both secondaries on the bottom. Okay? They are inversely related to the current. All right? So as the voltage goes up, the current will actually go down because there's one resistance. All right? That's basically what we are looking at here. So as the voltage goes up, sorry, that's not correct. They're just inversely related. As the voltage goes up, the current will go down. All right, is what we are looking at for this particular situation. N stands for the number of turns in the coils. Obviously, P and S are the coils. Primary coil is where it comes in. Secondary coil is where it leaves. All right, apologies about that. All right, so there is your relationship. All right. So for a step-up transformer, the voltage out will be greater than the voltage that comes in. The current out will be less than the current that comes in. And then the number of turns on the secondary coil will be greater than that on the initial coil. Opposite for step-down transformers. All right. So here's your example problem. You have a step-up transformer, so we know where it's getting larger. Okay, the voltage should go up. It has 200 turns on the primary coil, 3,000 turns on the secondary coil. So we're going to get quite a big jump. The primary coil is supplied by an effective AC voltage of 90 volts. What is the voltage in the secondary circuit? After we figure that out, what's the current in the secondary circuit? The current in the secondary circuit is 2 amps, so what's the current in the primary coil? So we got two problems here. All right. So what we do is we identify what we have, a lot of different information. Technically, we could answer either one first. The only thing that people mess up most of the time with this is obviously, where do the S and P go? Where does secondary go? Should they match up exactly, or should I inverse them? All right. So if I solve for voltage first, it's going to be Vs over Vp equals Ns over Np. They are directly related, so I should have S and Ps on the same side of the fraction. There's my numbers. The voltage out should be 1,350 volts. That's good because I should see it increase. That's another way to make sure you're doing this right. We should see an increase in voltage as a step up. As for current, though, it's going to be the opposite. This is the secondary over the primary, while this is the primary over the secondary. They are inversely related. All right? You can really flip this however you want. There's not one specific way, as long as, again, the individual variables line up appropriately. So for this one, it turns out we go ahead and solve. Okay? And the current will be 30 amps on the primary coil. Okay, 30 amps on the primary. It gives us the secondary coil in the problem. All right? So that is what we are looking for in both of these problems. Okay? Oops, sorry. So that is how we can solve transformer problems. You'll get some good practice with it. So again, always refer back to the individual formula itself. Try to think again, should it increase, should it decrease? All right? Obviously, this one's a little misleading just because of the way that we were looking to try to complete this one. All right? And again, understand that this was Vs. 1,350 was Vs, so we did have it as a kind of inverse relationship. The voltage increased while actually the current decreased from 30 down to 2. All right? That's a little confusing, obviously, to pick up on. But again, you'll always have the formulas. Just make sure you're plugging in the numbers in the correct spots. All right? Thank you.